This is Beyond the Business.
When people think about the environment, they usually imagine something visible. Forests disappearing, oceans filling with the plastic, rivers changing color near industrial zones. These images are powerful because they are physical. We can see them, we can photograph them. They become symbols of environmental change. But there is another layer of the planet that rarely appears in those images: the air. The atmosphere surrounds every city, every ocean, every mountain, and every industrial system on Earth. It is the medium through which weather moves, through which aircraft travel, through which clouds form and storms grow. It regulates temperature, distributes moisture, and connects ecosystems across continents. Yet, despite its enormous importance, the atmosphere has long remained one of the least visible elements of the global economy. Part of the reason is psychological. Human perception is naturally drawn toward objects and surfaces. We notice landscapes, coastlines, buildings, machines, and infrastructure. These are solid, measurable, and easy to map. Air, by contrast, appears empty. It seems like a background rather than substance. For most of human history, that perception made sense. The atmosphere felt vast and limitless. Winds carried smoke away from cities, rain washed particles from the sky. The scale of the planet seems large enough to absorb the byproducts of human activity without consequence. Industrial civilization quietly changed that relationship. Over the past 2 centuries, the global economy has expanded to a scale that previous generations could hardly imagine. Factories multiplied, energy productions accelerated, transportation networks spread across continents and oceans. Aviation opened the skies as a new layer of global mobility. All of these systems share something in common. They interact constantly with the atmosphere. Power plants release gases created during combustion. Aircraft move through a high altitude air corridors linking continents. Industrial processes emit microscopic particles and chemical compounds, and the cities generate heat and emissions that mix interregional air systems. Most of these interactions are invisible to the naked eye. A cargo aircraft leaving a runway does not appear to alter the atmosphere in any obvious way. A power plant chimney releases a plume that quickly disappears into the sky. A container ship crossing the ocean leaves little visible trace once it passes beyond the horizon. Yet, when these activities are repeated millions of times across the global economy, the cumulative effect becomes significant. The atmosphere slowly absorbs and redistributes the byproducts and industrial activity. Carbon dioxide mixes globally through atmospheric circulation. Methane released from agriculture and energy systems spreads through the same planetary currents that carry clouds and storms. Fine particles emitted by engines and industrial processes travel across borders and oceans. Unlike landfills or polluted rivers, the atmosphere does not accumulate waste in the visible piles. Its changes are subtle and distributed. They appear in shifting climate patterns, rising global temperatures, and the chemistry of the air itself. In other words, the atmosphere has gradually become one of the largest invisible repositories of industrial waste ever created. This idea may sound dramatic, but it reflects a simple physical reality. Every modern economy depends on energy, transport, and industrial production. These activities transform materials and release byproducts. Some of those byproducts remain with the economic system as products, goods of infrastructure. Others disperse into natural systems. And the atmosphere is the largest of those systems. For a long time, this relationship remained outside the core logic of economic thinking. Markets tracked commodities, labor, capital, and infrastructure. But the atmosphere itself rarely appeared on the balance sheets or supply chain diagrams. It existed as a background condition rather than as an active component of the system. Only gradually has the global conversation begun to change. Today, the atmosphere is no longer viewed simply as an empty space above the economy. It is increasingly recognized as a complex global system interacting directly with the industry, energy production, and transportation networks. Air traffic routes intersect with the climate systems, industrial emissions interact with the atmospheric chemistry, energy choices influence the long term composition of the air that surrounds the planet. This shift in perspective is one of the most important transformations in modern environmental thinking. It requires us to look at the atmosphere not just as weather or climate or environmental background. It asks us to see it as a part of the economic system itself. In the same way that oceans carry global trade and rivers support agriculture, the atmosphere has become deeply integrated into the functioning of industrial civilization. And once we begin to see it in that way, a new set of questions begins to appear. What exactly flows into the atmosphere as a result of economic activity? How does those invisible flows accumulate over the time? Why did the global economy treat the atmosphere for so long as an unlimited sink for industrial byproducts? And perhaps most importantly, what happens when this assumption begins to change? These are the questions that will guide the next season of this series. After exploring the hidden structures of the economic waste, energy systems, and ocean ecosystems, we now turn our attention to the most invisible layer of them all, the air. Because understanding the atmosphere may be one of the most important steps toward understanding how modern civilization actually interacts with the planet that supports it. To understand how the atmosphere became part of the economic system, it helps to step back and look at how industrial civilization actually works. Every industrial process is, as its core, a transformation of energy and materials. Coal becomes heat, oil becomes motion, gas becomes electricity, steel, cement, chemicals, and plastics emerge from complex reactions that reshape raw materials into products that support modern life. None of these transformations happen in isolations. They interact constantly with the surrounding environment, and the atmosphere plays a central role in that interaction. In the early phases of industrialization, this relationship seemed almost trivial. A factory burned coal to produce steam, the smoke rose from chimney and disappeared into the sky, and the atmosphere functioned as a giant dispersal mechanism, carrying emissions away from the immediate area. From the perspective of the factory owner, the process appeared efficient. Energy entered the system in the form of fuel, work was performed by machines, and the byproduct simply vanished into the air. For a long time, the scale of industrial activity was small enough that this perception seemed accurate. But industrial growth did not remain small. Over the 19th and 20th centuries, the global economy expanded at a pace that fundamentally changed the relationship between industry and the atmosphere. Cities grew larger, energy consumption increased dramatically, transportation systems connected continents, and heavy industries multiplied across regions rich in coal, oil, and mineral resources. And with every new power plant, refinery, factory, or transportation network, the atmosphere became more deeply integrated into the industrial process. Energy production provides one of the clearest examples. Burning fuel releases energy, but it also releases gases. Carbon dioxide, nitrogen oxide, and other compounds emerge as natural byproducts of combustion. When energy systems operate at the scale required by modern societies, these emissions are released continuously, day after day, across thousands of facilities. Transportation adds another layer to the story. Ships crossing oceans, trucks moving along highways, and aircraft traveling between continents all rely on engines that convert fuel into motion. These engines operate with the atmosphere itself. Their emissions disperse directly into the air currents that circulate around the planet. Aviation illustrates this interaction particularly clearly. Commercial aircraft operate at altitudes where atmospheric circulation begins to move air masses across entire regions. Emissions released at those altitudes don't simply remain near airports or flight paths. They enter large scale atmospheric flows that distribute particles and gases across long distances. Industrial production adds still more complexity. Chemical manufacturing, steel making, cement production, and other heavy industries generate a wide range of gases and particles as part of their processes. These emissions are rarely dramatic in isolations. They emerge from countless facilities operating simultaneously across industrial regions. Individually, each emission may appear small. Collectively, they represent one of the largest flows of material from the economic system into the atmosphere. This is where the idea of the industrial atmosphere begins to take shape. The atmosphere is not merely a passive background surrounding human activity. It functions as a medium through which energy systems operate, transportation networks move, and industrial byproducts disperse. In effect, industrial civilization has woven the atmosphere into its operational system. Air carries aircraft between continents, it disperses emissions from power plants and factories, it transports microscopic particles produced by engines and industrial processes. It mixes gases released by agriculture, energy production, and urban activity. All of these flows occur simultaneously. The result is a complex interaction between the global economy and the atmospheric system that surrounds the planet. For much of the 20th century, this interaction remained poorly understood outside scientific circles. Economists focused on productions and growth, engineers focused on efficiency and technological performance. Industrial expansion was viewed primarily through the lens of economic development. The atmosphere remained largely invisible in those calculations. It was assumed to be vast enough to absorb whatever the economy released into it. Only gradually did scientists begin to measure how these emissions accumulated over the time. Atmospheric monitoring stations started detecting rising concentration of carbon dioxide. Researchers studying air pollution documented the health effects of particulate matter in major cities. And climate scientists began modeling how greenhouse gases influence global temperature patterns. These discoveries did not immediately transform economic thinking, but they introduced a new idea that would eventually reshape the global conversation. The atmosphere was not simply empty space above the economy. It was a dynamic system responding to the cumulative influence of industrial activity. And once that realization began to spread, the relationship between industry and the atmosphere started to look very different. One of the most unusual characteristics of atmospheric waste is that most of it cannot be seen. When pollution appears in rivers or oceans, the evidence is often immediate. Water changes color, float and debris accumulates near coastlines, oil slicks spread across the surface of the sea. These events create powerful images that capture public attention and quickly become environmental symbols. Air pollution rarely behaves that way. Most gases released in the atmosphere are transparent. Carbon dioxide has no color. Methane cannot be seen. Nitrogen oxides disperse quickly through air currents. Even microscopic particles that influence air quality are often too small for the human eye to detect directly. As a result, the atmosphere can absorb enormous quantities of industrial byproducts without producing obvious visual signals. For centuries, this invisibility shaped the way societies understood pollution. Smoke rising from a factory chimney appeared dramatic when it was dense and dark. But once that plume faded into the sky, it seemed to disappear. The air above the city returned to looking clear, and daily life continued. The deeper reality is more complicated. Many substances released into the atmosphere remain present long after they vanish from sight. Carbon dioxide, for example, can remain in the atmosphere for decades or even centuries. Methane persists for shorter periods but has a strong warming effect while it remains present. Other gases participate in chemical reactions that influence atmospheric composition over the time. Microscopic particles create another layer of interaction. Fine particulate matter produced by engines, industrial combustions, and other processes can travel long distances through atmospheric circulations. These particles may eventually settle on the land or ocean surfaces, but during their time in the air, they influence both environmental conditions and human health. Unlike visible waste, which accumulates in landfills or polluted landscapes, atmospheric waste spreads through a moving system. Air currents constantly mix and redistribute gases and particles across regions and continents. A plume emitted from one industrial layer may be transported hundreds or thousands of kilometers before it becomes diluted with a wider atmosphere. This mobility makes atmospheric waste fundamentally different from most other forms of pollution. A plastic bottle discarded on a beach remains in one location until waves or tides move it somewhere else. Chemicals spill in the river flow downstream through a visible channel. But gases released into the air enter a global circulation system that operates continuously around the planet. In other words, atmospheric waste does not simply accumulate in a single place. It becomes part of a planetary system. This characteristic makes the atmosphere both resilient and vulnerable. Resilient because its vast scale allows it to disperse emissions across enormous distances. Vulnerable because the same dispersal process means that emissions released anywhere can eventually influence conditions everywhere. The invisibility of these processes has historically made them difficult to incorporate into everyday economic thinking. Factories produce goods that can be measured in tons or units. Transport systems move cargo that can be counted in containers or barrels. Industrial productions generate waste streams that can often be tracked through physical disposal systems. Atmospheric waste rarely fits neatly into those categories. It emerges as a byproduct of activities that are otherwise considered productive. A power plant generates electricity, an aircraft transports passengers, steel mill produces materials used in constructions. Each of these processes supports the functioning of the modern economy. Yet each of them also releases substances into the atmosphere. When viewed individually, these emissions appear insignificant. A single flight or factory operation does not visibly alter the sky, but the global economy consists of millions of such activities occurring simultaneously. The cumulative effect becomes a substantial. This accumulation is not always immediately visible in the daily experience. The atmosphere continues to look familiar, clouds form and move across the sky as they always have. Winds shift and storms develop according to patterns that have existed for centuries. But beneath that familiar appearance, the chemical composition of the atmosphere can slowly change. Scientific measure these changes through monitoring stations, satellite observations, and atmospheric modeling. These measurements reveal patterns that are difficult to perceive without instruments. Rising concentrations of certain gases, change in ratios of atmospheric components, subtle shifts in temperature patterns, and circulation dynamics. In this sense, the atmosphere functions like a vast archive of industrial activity. Every power plant, engine, furnace, and chemical process leaves a trace within the air that surrounds the planet. Over time, those traces accumulate and interact, forming patterns that reflect the scale and structure of human economic activity. Understanding this invisible accumulation is essential for understanding how modern civilization interacts with the atmospheric system. Because once we recognize that the air itself carries the byproducts of industry, the atmosphere begins to look less like empty space and more like a shared environmental infrastructure. An infrastructure that silently records the consequences of the global economy. If the atmosphere has been absorbing the byproducts of industrial activity for more than 2 centuries, an obvious question emerges. Why did it take so long for the global economy to recognize this relationship? Part of the answer lies in the structure of the atmosphere itself. Air does not belong to any individual company, government, or industry. It moves freely across borders and continents. Winds don't stop at national boundaries. Atmospheric circulation does not recognize economic jurisdictions. Because of this, the atmosphere historically existed outside the traditional framework of ownership and accounting. Factories owned their machinery, energy companies owned their power plants, and transport companies owned ships, aircraft, and logistics networks. But the air surrounding those systems belonged to no one in particular. This created what economists later began to describe as a classic externality. Industrial systems could release emissions into atmosphere without those emissions appearing directly in production costs. The economic transaction ended when electricity was delivered, goods were produced, or cargo was transported. What happened to the resulting gases in the atmosphere was not part of the accounting system. For a long time, this arrangement seemed natural. During the early industrial period, cities often experienced visible air pollution. Coal smoke darkened the skies above major industrial centers such as London, Manchester, or Pittsburgh. Yet, even in those conditions, the atmosphere was still perceived primarily as a dispersal mechanism. Smoke rose from factories and gradually faded into the sky, as long as emissions did not remain concentrated in a single location. The system appeared to function. One of the most famous historical examples illustrates this perception clearly. In December 1952, London experienced what became known as the Great Smoke. Combination of cold weather, stagnant air, and heavy coal burning created a dense layer of pollution that settled over the city. Visibility dropped dramatically. Public transportation slowed. Hospitals filled with the patients suffering from respiratory problems. Over several days, thousands of people died as a result of the pollution. The event shocked the public and eventually led to the Clean Air Act in the United Kingdom. But it also revealed something important, that air pollution had existed for decades before it became impossible to ignore. And the atmosphere had been absorbing emissions from coal combustions throughout the Industrial Revolution. Only when weather conditions trapped those emissions over the city did the consequences become immediately visible. Similar patterns appeared in other industrial regions. In the mid 20th centuries, Los Angeles developed severe smoke problems linked to automobile emissions and industrial activity. The city's geography, surrounded by mountains, allowed pollutants to accumulate under certain atmospheric conditions. The result was a brown haze that regularly covered the urban skyline. In Japan during the 1960s, rapid industrial expansion created serious air pollution problems in several cities. Industrial emissions combined with urban growth to produce health crises that eventually triggered stronger environmental regulations. Each of these examples followed a similar pattern. Pollution existed for years or decades before it became visible enough to trigger widespread public concerns. Until that moment, the atmosphere continued functioning as an invisible extension of the industrial system. Another reason for the economic blind spot was technological optimism. Industrial societies tended to view pollution as a temporary side effect of progress. As technologies improved, it was assumed that cleaner processes would eventually solve environmental problems. In many cases, that assumption proved partly correct. Advances in engine design, fuel quality, and industrial filtration systems reduced certain types of pollution significantly. Urban air quality in many developed countries improved during the late 20th century as a result of these technologies and regulations. Yet, even as a visible smoke declined in many cities, the broader atmospheric system continued receiving emissions from energy production and transportation industry. This is where the scale of the modern economy becomes important. Today, the global energy system consumes enormous quantities of fuel every day. Aircraft connect thousands of cities through international flight networks. Container ships move cargo across oceans. Trucks distribute goods through continental logistics systems. And power plants operate continuously to supply electricity to expanding urban regions. Each of these activities releases gases and particles into the atmosphere. Individually, the emissions appear modest. Collectively, they represent one of the largest continuous flows of material from the economic system into the natural environment. For a long time, the atmosphere's ability to disperse these emissions masked the cumulative effect. Unlike a landfill, which eventually fills to capacity, the atmosphere does not present obvious physical limits. It mixes and redistributes substances across a moving planetary system. But that mixing does not eliminate the material that enters the system. It simply spreads it across a larger space. Over the time, scientists studying atmospheric chemistry and climate systems began to understand how these dispersed emissions interact. Greenhouse gases influence the balance of energy with the Earth's climate system. Aerosols affect cloud formation and sunlight reflection. Particles influence both weather patterns and air quality. These discoveries gradually shifted the way the atmosphere was perceived. Instead of functioning as an infinite sink for industrial emissions, it began to look more like a shared environmental system with its own dynamics and limits. The blind spot of the industrial economy was not created by ignorance alone. It emerged from the combination of invisible processes, dispersed responsibilities, and the global system that initially appeared large enough to absorb human activity. Only when scientific observation revealed the cumulative patterns hidden with the atmosphere did the scale of that interaction become visible. And once those patterns became clear, the atmosphere could no longer be treated as an empty space above the economy. It had to be recognized as a part of the system itself. Once the atmosphere is viewed as a part of the economic system rather than simply the space above it, the entire relationship between industry and the planet begins to look different. The most important feature of the atmosphere is that it is shared. Every country, every city, and every industry operates with the same global layer of air. Winds circulate across continents, jet streams move weather systems between oceans and land masses, and atmospheric currents constantly mix those gases released in different regions of the world. This means that emissions produced in one location rarely remain confined to that location. Air masses move. A factory operating in one region may release gases that eventually disperse across entire hemisphere. Emissions from ships traveling across major ocean routes mix into the same atmospheric circulation that influences weather patterns thousands of miles away. Aircraft operating along busy international corridors release emissions into air currents that connect distant parts of the planet. The atmosphere doesn't function like a local environment, it functions like a planetary system. One of the clearest examples of this interconnected structure can be seen in global aviation networks. Every day, thousands of aircraft move through high altitude airspace, linking major economic regions. Flights depart from North America, Europe, the Middle East, and Asia in continuous waves. At cruising altitude, these aircraft enter atmospheric layers where large scale air circulation patterns distribute gases across long distances. From the perspective of the aviation industry, these emissions are part of normal operation. Aircraft engines release exhaust gases as a natural consequence of fuel combustions. But once those emissions enter the atmosphere, they become part of a much larger system of atmospheric chemistry and circulation. Shipping offers another example. Large container vessels travel along some of the most heavily used maritime corridors in the world. Routes between Asia, Europe, and North America carry thousands of ships every year. Each vessel burns fuel to propel itself across oceans, release exhaust gases into the surrounding air. Individually, these emissions may appear minor compared with the global industrial output. Yet, when multiplied across the entire global fleet, they form a continuous stream of atmospheric interaction between the logistic system and the planetary environment. Energy systems create even larger flows. Power plants generate electricity for cities, and industry operate around the clock. Many of them rely on combustion processes that release gases into the atmosphere as part of energy production. These emissions rise into the air, mix with the atmospheric circulation, and gradually disperse across regions. What connects all of these examples is scale. The atmosphere integrates emissions from countless economic activities into a single dynamic system. Aircraft engines, shipping routes, industrial plants, vehicles, and energy infrastructure all interact with the same layer of air. This is why the atmosphere can be described as the only environmental system shared simultaneously by every economy on Earth. Ocean connects continents through trade routes, but not every country has direct access to them. River supports agriculture and industry, but they are redistributed or distributed unevenly across geography. Forests and mineral resources belong to specific regions. The atmosphere is different, it surrounds the entire planet. Every human activity that relies on energy, combustions, or chemical transformation interacts with it in some way. Because of this, the atmosphere can be understood as a kind of invisible infrastructure supporting modern civilization. Transportation networks depend on it, aviation operates with it, weather systems influenced by atmospheric conditions determine agricultural productivity. Climate patterns regulate temperature ranges that shape human settlements and economic activity. When viewed from this perspective, the atmosphere becomes more than environmental background. It becomes part of the operating system of the planet, and like any complex system, it responds to cumulative pressure. Changes in atmospheric composition can influence temperature patterns, precipitation cycles, and the frequency of extreme weather events. These changes don't occur instantly or uniformly. They emerge gradually through the interactions between atmospheric chemistry, ocean circulations, and energy flows with the Earth climate systems. This complexity is precisely what makes atmospheric waste difficult to manage. Unlike a landfill or polluted river, the atmosphere cannot be cleaned by removing material from a single location. Its changes reflect the combined influence of countless sources distributed across the global economy. Managing atmospheric impact therefore requires a different type of thinking. Instead of focusing only on local emissions or individual facilities, the system must be understood at the planetary scale. Energy systems, transportation networks, industrial production, and agricultural practices all become part of a single conversation about how the global economy interacts with the atmosphere. This system perspective is relatively new in the history of industrial civilization. For most of the past 2 centuries, economic development expanded faster than our understanding of how the atmosphere responds to cumulative emissions. Industrial growth was measured primarily through production, trade, and technological process. Today, the conversation is beginning to include another dimension: how the invisible layer surrounding the planet interacts with everything the modern economy produces. Understanding that interaction is essential if we want to understand the real structure of industrial civilization. Because the atmosphere is not just the sky above the economy, it is the medium through which the consequences of the economy travel. When we look back at the history of industrial civilization, one pattern becomes clear. Human societies has always been skilled at managing what they can see. Cities developed systems to collect solid waste, rivers and coastlines eventually forced governments to regulate visible pollution. Industrial facilities learned to treat wastewater and control emissions that produced immediate health risks. Visibility creates pressure for action. When pollution becomes obvious, it demands a response. The atmosphere, however, has always operated differently. Most of the substances released into the air remain invisible. They disperse through complex circulation patterns and accumulate gradually over the time. Their effects are often indirect, appearing not as immediate disasters, but as slow shifts in environmental conditions. For much of modern history, this made the atmosphere easy to overlook. It was treated as a background rather than infrastructure, a limitless medium through which aircraft could travel, weather systems could move, and industrial emissions could disappear. Only recently has the global conversation begun to recognize how central the atmosphere actually is to functioning of the modern world. Energy systems interact with it constantly. Transportation networks depend on it. Climate stability, agricultural productivity, and weather patterns all emerge from processes taking place within the thin layer of air surrounding the plant. This realization changes the way we think about waste. Waste is often imagined as something solid, material that accumulates in landfills, oceans, or industrial sites. But a large share of modern economic waste does not look like garbage at all. It exists as gases, particles, and chemical compounds moving through the atmosphere. Invisible flows created by power plants, engines, industrial productions, and agriculture. These flows don't remain confined to individual regions. They mix across the global atmosphere, forming patterns that reflect the scale and structure of human economic activity. In that sense, the atmosphere has become one of the most important mirrors of industrial civilization. It records what our systems produce, how our economies move energy and materials, and how those activities interact with the natural systems of the planet. This reason of the series will explore that invisible layer. I will look at how aviation interacts with the atmospheric systems, how energy production shapes the chemistry of the air, how industrial emissions circulate through global atmospheric currents, and how economic systems are beginning to respond to growing awareness of atmospheric limits. Some of these responses involve new technologies, others involve new regulatory frameworks, market mechanisms, or international agreements. But all of them share a common starting point: the recognition that the atmosphere is not simply empty space above the economy. It is part of the system. Understanding that system will be the focus of the next chapter of the series. Because once we begin to see the atmosphere not as a background but as an infrastructure, a different picture of the global economy begins to merge. One where the invisible flows moving through the air become just as important as the visible goods moving across land and sea.